Hello everyone, it's yet another session of Nanoelectronics module 5 and this is the fourth session. So far we have completed one big section of module 5 which involved transport mechanism under the effect of an electric field. We studied parallel transport, hot electrons in parallel transport as well as perpendicular transport. And today in this session we shall consider two other topics, the quantum transport in nanostructures as well as Coulomb blockade. So let's get started. So quantum transport in nanostructures. Well, when we say quantum transport, it's nothing but transport mechanism in nanostructures when the nanostructure is connected to an external current. We may use a lead or other contact tips so that you can connect your nanostructure to the external current. Well, it may be a quantum wire, it may be a quantum dot, whatever be your nanostructure, you are supplying an external current to the nanostructure so that you can observe the quantum transport in the nanostructure. So far, see, when we were discussing about the transportation under the effect of electric field, we have not considered an external current or external contact in much sense. We were considering the transportation within the nanostructure when the nanostructure was under the effect of an electric field, right? So here in quantum transport we are going to consider nanostructure which has been connected to external current using contact lead. And this kind of transport we call it mesoscopic transport. I hope the term mesoscopic is familiar to you. It stands somewhere between the macroscopic and microscopic. So it's simply the nano scale transportation, just remember that. So if you want to observe the quantum transport effects in the semiconductor nanostructures, we must ensure few things. Number one is that the electron's effective mass should be small. What happens when the electron's effective mass becomes small? Obviously, they will have high electron mobility. When the mass of the electron reduces, they can more easily travel, which is, I guess that's clear, right? Another point is that the transportation in mesoscopic system must be ballistic. Why ballistic? When I say ballistic, it means that the transportation doesn't have any collision or scattering. Now, why will be the transportation in these nanostructures ballistic? Mostly ballistic. Since the dimensions of our devices are smaller, than your mean free path, the electron's mean free path, which means the chances of collisions are comparatively less. Compared to the bulk materials, the chance of collision of scattering is less, which means the transportation will have a ballistic nature because there is no collision. Right. So, for understanding the quantum transport mechanism, let's consider a one-dimensional mesoscopic system. So, here I have taken a quantum wire and the quantum wire has been connected to a reservoir on both the sides. Reservoir is just a source of current, and this is connected to the reservoir using contact or lead. Now, if the quantum wire is short enough, we can see that there would be no scattering and the transport will be ballistic in nature, and this is what we are intend to have. We don't want any kind of scattering so that the transportation is ballistic. So we are considering that the wire is short so that there is no scattering and your transportation is ballistic in nature. Now see, consider that one-dimensional quantum wire is connected to the reservoir through lead, and we consider that the leads are ideal, which means they do not produce any scattering effect. And each lead, the lead on the right and left, have their Fermi levels as say EF1 and EF2. So if you want a current flow through the quantum wire, we must apply a small voltage to the system, to this arrangement, right? So let a voltage V be applied between a reservoir. So here across this reservoir, across this, so across this reservoirs, I am applying a voltage V so that a current flows through this quantum wire, right? Now we have a voltage V, EF1 and EF2 are my Fermi levels of both these lead. In that case, the potential energy between the two reservoirs will be EF1 minus EF2, which is nothing but the difference in their Fermi levels. Now, let me find what amount of current flows across this wire. You can easily find the current as the product of the DOS function, the density of state function of a one-dimensional wire, and the electron velocity and a unit electronic charge, which gives our current as shown, I equal to E into N1D of E. Recollect, N1 N of E represents the DOS function. Since it is a one-dimensional structure, I represent it as N1D of E. V of E is the electron velocity and EV, electron volt. But we already have N1D of E given by 2 divided by pi h bar Vg. So this is something we are familiar with, we are already familiar with, since it is a one-dimensional nanostructure. We have already seen the derivation of the one-dimensional nanostructure. So using the equation for N1D of E in the equation of current, we get the new current as I equal to 2 times E square V by H. See, you can see that in this equation I have eliminated pi. How? I have replaced H bar by H by 2 pi, right? I hope that step is clear. So I have substituted N1D of E equation into this equation of current, obtaining this equation. Fine. So from here, let me determine the value of transconductance. So conductance is nothing but the ratio of current by voltage. So the transconductance can be defined, like obtained from this equation as I by V, which is nothing but 2 E square by H, and this is your transconductance. And here let me define this value E square by H by another value. Let me represent E square by H by G naught, which is the unit, quantum unit of conductance. So what have I done so far? I was considering the quantum transport in a one-dimensional nanostructure. For that, I have taken a quantum wire which was connected to 2 reservoirs on both its ends, on right and left. It was connected using 2 contacts. So the contact had a Fermi level of EF1 and EF2, which gave them a potential energy between the reservoirs as EF1 minus EF2. So in order to generate a current flow through this quantum wire, what have I done? I have applied a small voltage V between these reservoirs. I have defined the equations of current, substituted the value of N1D of E, the DOS function, obtaining a new equation for current, from which I have defined my conductance. Conductance G is nothing but I by V. So I defined my conductance as G equal to 2 E square by H, and this is the fundamental conductance. And from this I have defined the quantum unit of conductance G naught by E square by H. So G is nothing but 2 times G naught. That's it. See, we are just defining each terms, right? That's it. Don't have to worry. Okay, and once you get your conductance, you can get your resistance also. So resistance is nothing but 1 by conductance. So you can define R naught, your unit of resistance, the quantum unit of resistance, as 1 by G naught, giving you H by E square. I hope this is clear so far, right? So normally this value of R naught, H by G square, will approximately be like 25.8 kilo ohm or so, nearly 26 kilo ohm, right? So conductance will be 1 by 26 kilo ohm. Fine. Now let's see what happens regarding the subbands or the energy subbands in this quantum wires. It has a pretty interesting properties. So suppose we have several channels in this our quantum wires, and we can inject electrons in any channel. Say we have M channels, we can inject electrons through M channels, small m. Let me show you, yeah, this M. Let there be M number of ways by which electrons can enter your channel. Okay? And now these electrons, after interacting with whatever be the scattering particles present in your system, they can get out of this channel also. Suppose we have some kind of a channel here. The electrons are entering the channel through M different ways, and after interactions in this channel, they can get out of the channel through N different ways. That's what I am trying to say, right? So consider such a condition. So if we have several channels, the electrons can enter through M different way. After interacting with the particles, they can get out of the channel through N different ways. Then these electrons will contribute to a total conductance, which can be expressed like this. We have conductance as 2E square by H in the case of a single transition, right? But what is my situation right now? I have multiple number of channels, and I have multiple number of channels, N and M. So I'm not supposed to consider just one parameter. I have to consider the whole lot of parameter. So I have considered the transition probability, TNM square. So your total conductance will be that of one individual conductance and your total channel. I hope why this term came here, the reason is clear, right? Because we are considering several channels here. M ways to enter, N ways to get, which means we have a total of these many possibilities. So the total conductance can be represented like this. This is called the Landauer formula for conductance, where I guess this is not visible. This is the Landauer formula for conductance, where capital N is the number of quantum channels, the total number of quantum channels present in your nanostructure. Okay, so far what we have done is we have determined the Landauer formula for quantized conductance. We have considered a one-dimensional nanostructure connected to reservoirs, supplied voltage, found the current. We did few simplifications, got the conductance, what is the resistance, and finally we are considering multiple channels. and that's from that condition we obtained the Landauer formula. I hope this is clear so far, right? If so, then we are considering a new system. A new system in the sense, it's not a new system, we are familiar with it already. It's nothing but aluminum gallium arsenide and gallium arsenide interface, but it's something like a gate, the split gate between aluminum gallium arsenide and gallium arsenide. So what we can observe is that because of the shape of this gate, since the shape of this gate is like sloped, the electrons in this 2D plane are restricted to travel only through a small region in this in their one-dimensional plane. As a result, their electrical voltage distribution, as you can see here, the voltage and conductance distribution, has a step-like shape, right? Why is this so? Due to the special shape of this gate. This is nothing but your aluminum gallium arsenide structure. Our components are just the same. But what has happened? We have just considered this split gate alone, right? And because of this special shape of this gate, the relationship between the voltage and conductance of the electron is not continuous. We are taking very small steps because the electrons are, see, they are restrained in this very small region. Due to this confinement of my electrons in the small shape, the relationship between voltage and conductance has taken such a shape. This kind of structure is called a quantum point structure or the electron waveguide, because since just like a waveguide direct your waves, here due to this very small or confined opening, the electrons are directed through this gate only in a very small space, right? Now we can see that here the values of your conductance, they appear like some particular values, right? They are simply quantized. They occur as multiples of certain values. See this step which is repeated, which is repeated, which is repeated, which means this conductance values is quantized by an amount 2e square by h. So as your gate voltage increases, they increase as steps of 2e square by h. Here, this if there is a sharp step, the sharp step is not always easy to obtain, because they may get easily degraded because of maybe because of scattering events, impurities, resistance issues. So due to various reasons, the step size may get degraded. So that's about quantized conductance or quantum transport in nanostructure. So that's regarding the quantum transport in nanostructures. I hope it is clear. So what we did there was we defined or we obtained the Landauer formula for multiple channels, right? And we considered the split gate. What happens when a split gate affects on a normal heterojunction? What happens to the conductance? We saw that the conductance was in steps of 2e square by h, and how are the steps in IV characteristic degraded by. So what are the factors? We saw that. I hope this is clear. If so, we can move on to the next session, which is Coulomb blockade, which is a very important effect. So I need all of your attention, right? So basically in semiconductors we want a current magnitude to be very high. But what happens here? As we are scaling down our device size, feature size is reducing, because of which our current is also reducing. Now normally a semiconductor utilizes like many electrons. Say for some MOSFET devices, your electron concentration for 1 centimeter square area is nearly 10 raised to 11 to 10 raised to 12 electrons, which is a pretty huge amount of electrons in 1 centimeter square of MOSFET device. But what happens if you are reducing the size of a device further? In such situation, even a single electron can be involved for your device application. When your device size is reducing to a very small value, even a single electron can affect the device application. In such cases, changing one elementary charge in small nanometric systems has a great effect in their electrical and transport properties. This phenomena is called Coulomb blockade, and we can see how Coulomb blockade is obtained. So we are just saying that when your device size reduces very small, even a single electron can control their electrical properties, and this phenomena we call it the Coulomb blockade. And what happens for a Coulomb blockade? Now I want you to consider a semiconductor structure as shown. So in the previous section we have considered a quantum wire. Here we are considering a quantum dot. So just like the previous section, this quantum dot is connected to the reservoirs through leads. So they have a different potential Fermi levels EF1 and EF2, and their energy levels. Energy level is shown below in part B. You have the energy level, and this is your structure. In this structure we are trying to study the effect of Coulomb blockade, or how is Coulomb blockade obtained, and their energy levels are shown here. Let's see what does that signify. Well, let this show the energy level when there are n number of electrons in the dot, right? Now, if you want to change this number, capital N of electrons, how can you change it? You can just add one electron. N plus 1 can be the total number of electrons. If you want to add that one electron into this quantum dot, we want one electron to tunnel from this reservoir to this dot. Initially this dot has n number of electrons. I want to change the number of electrons in this dot, which means I just want to add one electron, which means I want one electron to travel from this reservoir to my quantum dot. I hope my purpose is clear, right? So how can you do that? For doing this transfer, what I am doing is I am applying a potential energy. I am applying a potential energy of certain electron volt to the electron by using an external voltage source. Now, if the total charge of the quantum dot, let the total charge be Q and let their capacitance be C, then we know their potential energy can be represented by Q square by 2C, which shows that an energy of at least E square by 2C must be provided to the electrons, so that this electron can enter from the left reservoir into the dot, which again shows that your voltage must be at least E by 2C. Right? So the charge on the dot is Q, capacitance C. The potential energy is given by Q square by 2C, from which we get, see, Q means in this charge. When it is electron, it is E. So E squared by 2C must be the energy provided to the electrons. And the corresponding voltage, what should be the corresponding voltage? It's obviously E by 2C. So the voltage, the external voltage must be increased to a value E by 2C to allow this transfer of electron from the reservoir to your dot. Now, if your, this got misplaced. If your electron voltage is, this is modulus of V, I'm sorry for that. If the modulus of V is less than E by 2C, which means when your voltage is greater than minus E by C but less than E by C, the electrons can't tunnel, which means there is no current. Was that clear? If the electron need to tunnel from the reservoir to your dot, the minimum voltage to be supplied was E by 2C. If the voltage was less than E by 2C, in this range, then the current flow will be 0. This is called Coulomb blockade. In this voltage range between minus E by C and E by C, the current will be 0, and this is called Coulomb blockade. Please let that digest. Yes? Okay. When this process continues, I am applying more and more voltage. I am keeping on adding more and more electrons. Initially it was just 1 electron. I am adding another 2 electrons, 3 electrons, 4 electrons. When I keep on doing this process, we can see that there will be discontinuities in your graph, because this is a Coulomb blockade. Simple. Whenever your voltage is 1 by 2C, 2n plus 1 times E, at all those voltage levels, you can see Coulomb blockade, because of which your graph is not continuous. You have a step size shape in the graph. Now, as you reduce the size of the quantum dot, their capacitance gets smaller, the value of the energy increases, because energy is Q square by 2C. So as C decreases, energy increases. Thus Coulomb blockade is more observable. So as a result, we have C must be less than E square by kT. So what do we intend to have? We need a small value of C so that our energy increases. Because of this, you can observe Coulomb blockade in a more visible manner, which means the voltage range increases, right? So to make it more observable, we must have C less than E square by kT. So for this, either you need the capacitance of the dot to be very small, which means the dot size should be very small, or we need the temperature to be less than 1 Kelvin. So to get your capacitance smaller, and by getting your temperature less than 1 K, we can ensure the visibility or the observability of Coulomb blockade. Another way to do that is to ensure that the number of electrons in the dot, they do not fluctuate when it is in equilibrium. See, we are trying to increase the number of electrons or change the number of electrons in the dot. But when your structure is in perfect equilibrium, we do not want the number of electrons in the dot to change. Yes. So if these two conditions are ensured, we can see that Coulomb blockade is more observable. Now let's just observe the resistance and the conductance in the case of a Coulomb blockade. So for that, let's consider the time taken for the electron to transfer to the dot or out of the dot, into the dot or out of the dot. Let it be R into T into C. See, RT into C. I'm sorry for that. So it's nothing but R into C. We have our time constant as RC. That's the same thing that I have taken here, right? R into C. Where here RT represents the resistance of your tunneling barrier. I guess you remember seeing that small barrier. So it is the resistance of this small barrier, and C is the capacitance of your dot. So let RTC be the time taken by the electron to transfer in or out of the dot. Now the fluctuation in the number of electrons in the dot obviously induce a potential energy of the order E square by C, which we have seen already, right? Now according to our uncertainty principle, we have delta E into delta T must be greater than H. From the value of delta E delta T, we can rewrite this as E square RT by C must be greater than H. See, what have I done here? Right, delta T, yes, and delta E, I have given this E square by C into RTC. Fine. So delta E into delta T change to this. I can rearrange this. I can cancel these C's. So I get E square RT by E square RT is greater than H, from which I further rewrite it as RT must be greater than H by E square, giving you an approximate value of 25.8 kilo ohm. See, just substitute the value for H, Planck's constant, and for E. So you get an approximate value of 26 kilo ohm, and from which we can get the transconductance G as very much less than E square by H. It is nothing but the reciprocal. So when you take the reciprocal, the inequality sign gets opposite. So 1 by RT, which is G, less than E square by H. This gives you your transconductance. That's about Coulomb blockade. So we saw what is Coulomb blockade. So it's simply that as your device size is getting smaller, even a single electron can change the properties of your device. So to analyze that, we just considered a quantum dot connected to reservoir and an external supply. We tried to plot the voltage and current. So we found that when the voltage was in between minus E by C and E by C, there was no current, which means in that region the current was blocked, and this phenomena we named it the Coulomb blockade, right? Fine. And later we analyzed their effect, so that when does this Coulomb blockade become more observable? So for that, what are the conditions that we need to follow? For that, we saw that the value of capacitance must be small and the number of electrons in the dot must not fluctuate in equilibrium. So given these conditions, we obtain the equation for resistance and conductance. That's what we have done so far. So in this session we discussed about Coulomb blockade and what was that other one? Yeah, and also we saw the quantum transport in nanostructures. By this we are completing two main sessions of module 5, and the last part of module 5 will discuss the transport mechanism under the effect of a magnetic field. So far it was electric field and voltages. Next we will discuss the effect under magnetic field. For the time being, thank you.